Hello everyone, welcome to Rational Science. Today we're going to be looking at physics. What is physics? Are we even in the right subject matter? Okay, that's what we're going to be looking at today. Here's a rundown. Is this what physics is about? Is it about inventing something, inventing a gadget? How many physicists do we have on Earth? Inventing. How many have we had? Inventing stuff every year, every day almost. Is it about discovering? The other day I said, you run into a rhinoceros in the jungle. You discovered a rhinoceros. The first man to discover a rhinoceros. Okay, you get a Nobel for that. You're doing physics. You're the first one who went outside and discovered that it rains. Oh, it's raining. You're a physicist. You discovered that it rains, right? Is it about measuring? You measure the table 100 times ever more accurately. And you develop gadgets. You invent some gadgets to improve your accuracy, your precision. Okay? Is that what physics is about? And then, give me a second here. Is it about coming up with an equation? So E equals mc squared, F equals ma. You're a scientist because you discovered an equation. What is an equation, if not a description? If you're just going to describe mathematically, quantitatively, you're saying 1 plus 1 equals 2. That's all you're saying. You're saying that a chair has 4 legs, and you deserve a prize for that. You're doing physics because you said that a chair has 4 legs and a backrest. 4 plus 1 plus 1, if you include the seat, maybe 2 armrests. So it's 4 plus 1 plus 1 plus 2 equals chair. That's physics. Is it about describing something, in general terms, qualitatively or quantitatively? It's just describing, I observed, I saw. What is physics? Is it about giving prizes, which is what the Nobel Prizes do? Let's find out. Let's find out what physics is about. Okay, and what I'm going to do today, I want to start with the people who won Nobel Prizes from 1911 to 1920. The other day I did 1901 when the prizes started to 1910. Today we're going to continue with the next 10. Okay, so let's see who the first one was. Here in 1911 we have Mr. Wilhelm Wien, or Wien, for his discoveries regarding the laws governing the radiation of heat. That's what he got his Nobel for. Okay, radiation of heat. When a completely dark body is heated, it emits visible light and other electromagnetic radiation. The spectrum of the radiation is entirely dependent on the temperature of the body and not its composition. Okay, in 1893, Wilhelm Wien formulated his displacement law, which indicates at which wavelength the radiation is most intense at a certain temperature. And here on the right, you see a little synthesis of what Mr. Wien discovered. Essentially, there you see that the bottom says the higher the temperature, the shorter or smaller the wavelength. And the lower the temperature, the longer the wavelength. Okay? There's the equation, okay, which says it's an inverse relationship between wavelength and temperature. Well, what he discovered is an equation that relates to the rope model of light. He never discovered it, what light is. So he's talking about radiation, meaning light, but he doesn't know what he's talking about. He's maybe thinking waves, but there is no physical object called a wave. Wave is what something does. You got to identify that something. And Mr. Wien did not discover that. In fact, no one has to this day. So what is the point of saying that, you've got the equation, or that you went to the lab, you measured, and this is what you saw, and then you put it in a paper, you publish your paper. And what have you done? Well, you've analyzed a ghost, a spirit. You put an equation to a spirit because you don't know, again, what that invisible entity is. It could be a turtle and it could be an eagle. And until you decide which, you may be applying your equation to something that you don't understand. You could be developing equations for turtles, and it turns out that Mother Nature does it with eagles. So this is a problem. Okay, this is a serious problem in mathematical physics. They're groping in the dark. Okay, they have no idea what they're applying their equations to. They're assuming that what Mother Nature does is run with particles or waves. There are no such things as waves, And the particles, it's not a particle. It's not a corpuscle. So we have no physical objects today. All we have is equations for something we can't see and we cannot even imagine under the classical or quantum mechanics. Okay, next fellow who won a prize. This was in 1912. And his name is Gustav Dalen. Now, the issue with this gentleman is that he was Swedish. And the prize is Swedish. So keep that in mind. It might help you understand, okay, well, why he got the prize. It turns out in 1912 he went blind because he ran an experiment in his lab and it blew in his face. So he was blinded after that. Anyways, it says, for his invention of automatic regulators for use in conjunction with gas accumulators for illuminating lighthouses and buoys. Lighthouses and buoys? What the hell? Does this deserve a Nobel? Is this what physics is about? It says, for centuries, lighthouses have made navigation safer. Okay, in the 19th century, acetylene gas began to be used to light their beacons. Okay, Gustav Dalen developed a method for emitting short flashes of light, thereby reducing gas consumption. Okay, so he saved on gas. Whatever he did, he saved on gas, right? In 1907, he invented a regulating valve. Whoa. Based on the difference in expansion between black and white metal rods. This solar valve could extinguish beacons during daytime, saving more money. Well, again, it's what I said the other day. Here you have these folks. Can you get them up here? And I think their inventions were a lot more important than lighthouses. I mean, one guy invented the telephone and opened up an industry that even lasts till today. The telephone is big business and has been ever since we've discovered or invented the phone. Edison, he invented or developed, essentially, he came up with it little by little, the filament for the bulb, one that he could commercialize. I think that was more important than lighthouse valve. And then the Wrights, they invented the airplane. They really broke their head. They went out there in they were from, I think, Dayton, Ohio, and they created a wind tunnel inside their lab or their garage or whatever. And then they flew their airplanes in Kitty Hawk in North Carolina. And, I think those inventions were a little more important than a lighthouse valve that saves on gas. And again, is this what physics is about? Or is this a political prize because the guy went blind and he's Swedish and he did a lot of work for the Swedes? He said, hey, we have no one else to give the prize to. Let's give it to this guy. Okay. Sounds more like that. Okay. How about 1913? Here we have this gentleman. And his name is Heike Onnes. How's Onnes for a name? Onnes or Onnes. For his investigation on the properties of matter of low temperature, which led inter alia to the production of liquid helium. So he discovered how to produce liquid helium. You just cool it down sufficiently low and you get liquid helium. And it says in 1911, Heike discovered that the electrical resistance of mercury completely disappeared at temperatures a few degrees above absolute zero. So he cooled down mercury and now he says there's no resistance. And they say, okay, that's the origin of superconductivity. Okay, he discovered it. Could he explain it? I mean, could he tell me why that's the case? What's happening inside mercury that makes it it turns it into a superconductor at low temperatures? Can he explain that? The reason, the cause, the mechanism? And so again, the fact that he can that he cools something down and discovers some properties. Well, here, I hope I get a Nobel for this one, okay? Keep this in mind. Here it is, okay? You saw it here first. Never saw it anywhere else, okay? Boiling water. I figured out that if you heat water long enough, at some point, it's going to bubble. Okay? So give me my Nobel. I mean, this is what Heike did. He just went in there. He says, okay, let's cool this thing down until we get a low temperature, okay? And low enough that we can see some properties. What properties did he see? Well, helium, which is a gas, turns into a liquid. And mercury at low temperatures loses its resistance. Okay, so and I figured out that if you boil water, you get bubbles. And it's hot. I tried putting my finger in it. I don't do that again. I mean, what is this? Is this what physics is about? Just observing something, an effect that you did in the lab. You heat something or you cool something and you see an effect and you say, oh, give me my Nobel. I know physics. These people could not explain what they did, and that's what I'm questioning. Okay, let's see who's the next fellow on the list. This is 1914, start of the World War I. Okay, we have Maxwell and Laue, and for his discovery of diffraction of X-rays by crystals. Okay, so he's going to point an X-ray at a crystal, and he's going to produce these diffraction patterns. Okay, says Maxwell and Laue came upon the idea that X-rays passing through crystals might create similar patterns. Diffraction meaning he did the slit experiment with X-rays through a crystal. Essentially, that's what it did. And so he found out that that they disperse, and you have this diffraction pattern. Okay, experiments confirmed Max Laue's idea. This demonstrated that X-rays could be described as waves. Well, yeah, they could be described as waves. Are they waves, or maybe something else like particles? I mean, you had, even before him, 1901, Max Planck had already discovered, that X-rays, essentially, not X-rays because they didn't know much about X-rays at the time, but that light, and X-ray is a portion of light, that light comes in discrete packages called quantum. That's when quantum started. And so what is this nonsense about waves? I thought we settled it's particles. Some kind of discrete unit of some kind. A wave is something that's elongated. Has no beginning, no end. They never talk about that. Does the wave from Andromeda stretch all the way from there to here? Or does the little wave have a beginning and an end? Is it a little sailboat that travels from there to here? They never explain that. Whether, this wave thingy extends all the way or travels. Can you chop a wave? That's the question. At beginning and end and send it out like a sailboat. And so he never clarified that. He never figured that out. He never understood that. He gets a Nobel saying, oh, he did physics. What physics did he do? Well, he discovered that, again, a diffraction pattern if he points the X-ray at a crystal. And that's, again, like boiling water. I boil water, so give me my Nobel. Here's the diffraction pattern. You'll see it here. Okay, essentially, he's got a crystal, which is what you see at the bottom, all these atoms there. And he's going to point the X-rays at different angles, and he's going to get a diffraction pattern on the wall. Okay, and diffraction pattern you see there, constructive interference and also destructive interference. That's essentially what he discovered. And again, it's a discovery. First, it's a discovery simply by testing something in the lab. Second, he did not explain why that's the case, why these diffraction patterns occur. Okay, and here you have essentially the same thing. When you shine a light through a prism, well, you get all these colors. Okay, it's not exactly diffraction, but what you get is something on the outside, and it's a different. You get the rainbow. Okay, and so the question is, well, is light a wave? Is it a bunch of particles as seen on the upper right there, or like on the bottom right, which you see the rope model? All right, which one of these is the correct? Will the real wave please stand up? Will the real mediator of light please stand up? Which one is it? See, the rope at least can explain why the velocity of light is constant and why frequency is inversely proportional to wavelength. What can these other two? What can the wave and what can the particle models explain? Okay, so Max did not do a good job in explaining anything. All he did was describe mathematically. Of course, you got to do it mathematically if you want a Nobel. Is that physics? Is it discovering something in the universe, some behavior of something invisible like light or gravity without understanding what it is? So these people are groping in the dark and they're just measuring the effects of that, what is visible, what is detectable, and putting an equation and saying this is how the entity that I can see and detect, that's how it reacted. So they look at the result and they measure that, they put an equation to represent that phenomenon, that observation, and then they publish and get their Nobel, and they say, I did physics. And still, they're groping in the dark. They still don't know what light is. They don't know what gravity is. They don't know what magnetism is. They don't know what any of these are, but they did physics. You see where I'm coming from with all this? Okay, here's 1915. Let's see what this guy invented or discovered or whatever. It's father and son team. First father and son team, or only, I think, that won the Nobel. And says that after Max von Laue discovered that diffraction patterns occurred when X-rays pass through crystals, this inspired William and Lawrence Bragg Okay, the two Williams, because they were both, one was Henry and the other one was Lawrence, father and son. Junior is the guy on the right. And it says they decided to conduct their own studies in the area, and their contribution included establishing the relationship between the wavelength of the X-ray, its angle of incidence, and the distance between the atomic layers inside the crystal. So far, all we have descriptions. They were able to tell how far apart the atoms were inside the crystal because they were able to use this diffraction phenomenon, which nobody understood anyways, even since the days of Thomas Young. And here you get an idea of what I'm talking about. Okay, this is what they try to do. They said, look, if you have, if you shine this X-ray on a crystal, okay, if it hits one atom, it's going to bounce off. Whether it's the particle or the wave, it doesn't matter. It's going to be detected at some place. And another wave or another particle, they did it with waves, and they claim it was proved the wave nature of light. The wave hits another atom, but it's offset. So one of the two. If the two atoms are too close together, half a wavelength together, then the waves are gonna interfere with each other destructively. And if they match, well, then it's going to be constructive interference. And so they said, well, this tells us how far apart the atoms are within the crystal, which was pretty neat. I'm not saying it's not, but I mean, what do we know about light? Or what do we know about X-rays, which is, you know, a portion of the spectrum of light? What have we found out about light, about the nature of light? We're trying to discover the nature of light. These guys are just measuring stuff and saying, look, I measured and found that this guy is half a wavelength off and this guy is one wavelength off because I can see these patterns on the screen or on the detector. So you either have constructive interference or destructive interference. You get the so-called fringes, you know, that you've seen in the slit experiment. And so with that, you know how far apart they are because you are able to measure in terms of wavelength how far apart one atom is from another. Okay? Now, yeah, you got to take your hat off to that, but they have not been able to explain why, the cause. Why is it so? Okay? All they have is a description. They say, well, this atom is a mile away from this other atom. Okay, so, yeah, it helps you see what's inside a crystal without seeing. You just deduce it, infer it. In that sense, it's good. But you still haven't explained, you know, anything with it. You're just describing that one atom is far away from another atom. That's all you're doing, the distance between atoms. Okay? And the question is that physics? Okay, here's the next fellow. And he got his in 1917 because in 1916 there was no prize. Remember there was a war going on? Okay, so, and I think he got his medal, even though it was awarded in 17, he got it in 1918 because, again, the war was on. Okay. Anyways, he says, or Nobel says that Barkla got his Nobel because for his discovery of the characteristic Röntgen radiation of the elements. Okay, what are we talking about here? Well, it says Barkla showed that each element's secondary spectrum was unique, okay, irrespective of temperature, structure, and chemical composition. Okay, you know, I mean, again, it's a description. We haven't explained any, he cannot explain why. That's my point. He cannot explain the cause, the physical mechanism, that invisible physical mechanism that Mother Nature uses to produce this effect. All he can do is describe it. And so the question is, are all these descriptions and inventions and to be able to see further, to be able to describe in more detail, is that what physics is about? Is this progression of technology coupled by description, mathematical description, or even qualitative description? Either way, it doesn't really matter. But going from technology to description, moving along, is that what physics is about? Or is that about technology? I mean, technology we developed, no doubt about it. We improved on the airplane. We don't have the same airplane that the Wrights have. We improved on the light bulb, you know, and on the telephone. We improved all these over time. So that's technology. That's a different realm. Is technology physics? Is physics technology? I mean, if you ask the military, they'll say, yeah, because we got the bomb. And all these guys did whatever they did. We don't understand any of that math, but they ended up with a bomb, and we love that. Okay, so they got the bomb. That's technology. Is that physics? I mean, if you don't understand how the bomb really works inside it, okay, because they don't, because they're doing it with particles, that's how they're explaining it, And it turns out that they can't explain it with particles because they can't explain the particles to begin with. They cannot explain the atom. They cannot show you their atom. They cannot tell you why the electron bead doesn't fly away from the nucleus, or why it doesn't fall inside the nucleus. Why does it orbit at a given distance? I talked about energy levels. Why is it here or there? Because that's the modern version, that the electron can be anywhere within a region. Fine. I don't care about all that. I want to know why the electron doesn't fall to the nucleus, or why does it fly away spontaneously. That's what I want to know. And they cannot explain that. Therefore, their explanation of how the bomb works is irrelevant. Okay, all they're saying is mathematically they can describe that from one atom you can get a Big Bang. That's all they can do. They have not explained the cause, the mechanism. All they can do is mathematically say, we do. It's again like boiling water. At 100 degrees centigrade, it boils. That's all they did. And I can put the equation there saying, no, 100 degrees C equals boiling. That's all they can do. That's a description. You're not telling me why, what's causing that to happen yet. Okay, so with the bomb, you can't say that you're going to use the atom, the quantum atom, to explain how the bomb works. That's my point. Okay, here's the next fella. It was Mr. Max Planck. Okay, and he made his discovery of the so-called quantum of light in 1901. So he preceded all these folks. He preceded all their nobles. We're talking about 1911 to 1920, right? So he discovered this 10 years earlier, 1901, that light comes in discrete packets called quantum, a little package of energy. And all these other people, they dealt with X-rays. They're talking about waves. What do you mean waves? We've already proved that light comes in particles, in chunks. So what is this wave thing? Why are they giving Nobels to people who are inventing stuff that no longer has any validity, because this guy already proved that light comes in chunks, in packets? We have a contradiction, because this guy now receives the prize the next year after these other guys prove that X-rays are waves. And this guy now says, no, you're all wrong. They're particles, and I proved that already 18 years ago, in 1901. So what do we have here? Do we know what light is? Is it X-rays or whatever? Are they light? Are they particles, or are they waves? We still don't know. Okay. So so it says, what did Planck get? He says, solved this problem in 1900 by introducing the theory of quanta. That is, that radiation consists of quanta, meaning little chunks. That's what he got his Nobel for. Okay. And again, if light consists of quanta, of little packets, of packages, or chunks of energy, whatever that may be, well, then that destroys all the X-ray people, which is what we've heard most of these for now, until now. Okay. Who came? Here I've got. See here again. Here's the atom, and it turns out that in 1944, Planck, many years later, right? He says the following: as a man, this is what he wrote. He gave a presentation in Italy, and it says, as a man who has devoted his whole life to the most clear-headed science, to the study of matter, I can tell you as a result of my research about atoms this much: there is no matter as such. Okay, so he's saying there is no such thing as matter. So what is an atom? What is all that stuff? What is a table? He says, all matter originates and exists only by virtue of a force which brings the particle of an atom to vibration and holds this most minute solar system of the atom together. We must assume behind this force the existence of a conscious and intelligent spirit. This spirit is the matrix of all matter. Now, how's that for a guy who spent his life studying the atom, okay? So he says, there is no such thing as matter, but we have these particles. Well, I thought particles is what we call matter. And so he says, yeah, but the matter, this particle is just a vibration of something that he calls, I guess, a spirit, a ghost, invoking, the heavens. He does this in 1944. That means until 1944, no one had figured out what an atom is, really. Yeah, because here he's saying, he's one of the top guys, and he's saying, we don't know what matter is. It's some kind of vibration, and there's nothing really there. The atom itself is just a vibration. And that's eventually going to lead to these guys with string theory. He says, your proton, your electron, they're not really particles. It's a vibration of what? A line. What kind of line? Is it a two-dimensional line? No, it's a one-dimensional line. It's a mathematical line. It's a geometrical line. An abstraction which does not exist in reality, but that's what they model the graviton especially with. They have this vibrating particle, line. And when you go into it, it's a mathematical line. And this mathematical line vibrates in 3 dimensions simultaneously, up and down, sideways, and in every direction at the same time. Is that what this line is? You know, that's all mathematics. They can do that mathematically. Please explain the real world. I need to know what is real out there. Well, I mean, physics is about reality, about existence, what exists out there in this invisible world, intangible world we can't see or touch, gravity and magnetism. I need to know what's in there. And the only reason these people haven't figured it out is because they can't see or touch it, the mediators. And so they came up with all this math, which is irrelevant if they're going to apply it to particles or to waves. This is where the problem is. So we have equations, and we have particles and waves, and none of it makes any sense. And they say, well, we'll never understand how this universe works. That's their conclusion. And 1944, many years after studying here, Max said, he gave up, essentially. He said, we'll never understand that. Essentially, it's a vibration of some ghost out there. That's what light is. Okay, next fellow. Here we have this gentleman. His name is Starke. Johannes Starke, German fellow, and he said, for his discovery of the Doppler effect in canal rays and the splitting of spectral lines in electric fields. What happened was that, here were 2 fellows. Let me get these fellows up here. Let's invite them to the talk here. And they won the Nobel Prize in 1902. One is Peter Zeeman, and the other one is Hendrik Lorentz. A lot of people know Lorentz. I don't know as many people know Zeeman, but he invented or discovered the Zeeman effect. What is it? Splitting of spectral lines into several components in the presence of a static magnetic field. And there you see this is a modern version. You see no magnetic field there. And when you put a magnetic field, you see how those fringes change. It splits the spectral lines. That's essentially what he discovered. Again, he boiled water and he found out it bubbles. That's what he did. And Hendrik supposedly explained it, but all he did was just give more math to the same thing. That's why he got half of the Nobel. Okay, so what did Starke do? Well, he did the same thing. He said, hey, these guys got a Nobel for that. I'm going to do it with electricity. So he took it and he said, splitting of spectral lines into several components in the presence of an electric field. So he went in there, he did electricity and got a Nobel for doing the same thing these other guys did in 1902. Again, he could not explain it. He had no spark. No, Starke did not have any idea what he was doing. All he did was describe it mathematically. He got an equation, okay, after doing his lab work. So he observed what he could see, not what he could not see, and then he applied his equation to that effect, and he called it the Starke effect. Okay, it's like the boiling effect, the bgaede boiling effect. When you boil water, it bubbles at 100 degrees, right, centigrade. This is what these people do. None of them were able to explain any of what they did. All they did was describe and say, I found a new effect. I observed. What did you observe? Well, I observed the invisible, intangible world of Mother Nature. Oh, you did? Did you observe that? Did you touch it? No. Actually, I just saw what was visible and tangible. I could not see the invisible and intangible. And so here's the equation that describes the effect on visible and tangible matter. That's what these people did. Okay? And here, let me give you an idea of, because he did it with magnetism and with electricity, and here we are today, and these people have no idea, what magnetism is. And if you go back in time, you'll find out that someone who deserved the Nobel Prize in 1269, 13th century, okay, was this gentleman, and his name was Petrus Peregrinus. Okay, he should deserve a Nobel Prize. Well, I believe for his discovery that the north pole of a magnet attracts the south. How's that for a discovery? Okay, here the Zeeman effect. They discovered that a magnet, changes the spectral line somehow. They don't know why. They don't know what physical interaction is going on in there, but they described, and mathematically, of course, right? They described what happened. They get a Nobel for that, for describing they're doing physics. Well, how about this guy? This guy said that north attracts south and south rejects south. Okay, and here is his his paper, his published paper. Okay, this Mr. Peregrinus, he says, if you wish, he says, how a lodestone attracts iron. Okay, chapter 8. If you wish the stone according to its natural desire to attract iron, proceed as follows: mark the north end of the iron, and towards this end approach the south pole of the stone. when it will be found to follow the latter, okay? Or on the contrary, to the south part of the iron present the north pole of the stone, and the latter will attract it without any difficulty. Should you, however, do the opposite, namely if you bring the north end of the stone towards the north pole of the iron, you will notice the iron turn around until its south pole unites with the north end of the lodestone. The same thing will occur when the south end of the lodestone is brought near the south pole of the iron. Okay, now does this deserve a Nobel Prize or what? Okay, I think he does. I mean, he's in the same tradition as all these people in the early 19th century. I mean, he discovered something. He doesn't know what he discovered. He says north attracts south. He could have called it X attracts Y for all we care. And if you turn it around, then it's Y hits against Y and they don't like each other, or X hits against X. Okay, so that's an observation. What caused it? That's the problem. See, these people don't understand what caused it. They just describe what they saw. And for that, they get a Nobel. And they say, I'm doing physics. Okay? So, yeah, today we do have an explanation. Okay? So, again, for all those people who think they are physicists, if you cannot tell me how a magnet attracts another, like here in this case, let me show you. Okay, here's two magnets. You got a little round circle there. Those are two magnets. And then you see. Now, you can see it sticking, and put it again, it sticks. Okay? You cannot tell me how that's done, how Mother Nature does that. You're not a physicist. Because we already have an explanation for this. You know, at least one explanation. I don't know if there are others, but that's up to you. If you have a better explanation, bring it on, you know. Particles, waves, whatever you got, just bring it on. And please don't go to Ken Wheeler. He had no clue either. He does it with, counter space. Okay, so he's no use. He's going to be no help to you to tell you how a magnet works. Okay, but here it is. This is today. This is what we know about magnets. Okay, and it says, how do magnets attract and repel? This is after what Peregrinus was 13th century. We're in the 21st century. This is what we have today. How do magnets attract and repel? Well, it says, the first one from sciencing.com. All magnets have two ends, which are commonly referred to as north and south poles. Ooh, it sounds a lot like Peregrinus. The determining factor of whether a magnet attracts or repels is the pole. Whoa. Magnets attract when a north pole is introduced to a south pole. If like poles are introduced, either north to south or south to north, the magnet repels. Okay, I love that. Not much progress since Peregrinus, and that's in sciencing.com. Let's see, National Geographic. Let's see if they can do better. Magnetism is caused by the motion of electric charges. Aha, this is a little different, okay? Every substance is made up of tiny units called atoms, okay? Each atom has electrons, particles that carry electric charges, okay? Spinning like tops, the electrons circle the nucleus, okay? I don't know why, but okay, let's continue. Or core of an atom. Their movement generates an electric current and causes each electron to act like a microscopic magnet. Well, we still don't know what an electric current is, you know. I mean, what do you mean an electric current? What is that electric current? And I mean, how does the movement generate an electric current? And then we don't know why it acts like a microscopic magnet, because we're trying to explain what magnetism is. And so you say, well, it behaves like a tiny magnet. Okay, great. Okay, what does that mean? What is magnetism? It's something that acts like a magnet. Okay. In substances such as iron, cobalt, and nickel, most of the electrons spin in the same direction. Aha. Okay. This makes the atoms in these substances strongly magnetic. I don't know why yet. Okay, but let's continue. But they are not yet magnets. Okay, good. We don't have magnets yet. Then what is magnetism? All magnets have north and south poles. Opposite poles are attracted to each other while the same poles repel each other. So, and that's 21st century. We're still with Peregrinus. We haven't abandoned poor old Peregrinus. He should deserve a Nobel for his tremendous discovery. Okay, how about the how stuff works site? It says how magnets work. Since paired electrons spin in opposite directions, Pauli exclusion principle, their magnetic fields cancel one another out. Okay, great. We don't know what a field is. Maybe someday we'll figure it out. Atoms of ferromagnetic elements, on the other hand, have several unpaired electrons that have the same spin. Okay, so we have same spins and opposite spins. Great. We got spinning tops. We got two tops. Two of them spin in the same direction. Two tops spin in opposite directions. That's what we have so far. Let's find out. Magnets attract materials that have unpaired electrons that spin in the same direction. Well, why? I mean, I have two tops, okay, and they spin in the same direction. One does not attract another. So why would electrons spinning in the same direction attract each other if these electrons are, discrete particles? Maybe vibrating strings? I don't know. So if they're spinning in the same direction, why would one electron. Why would one top affect another? In fact, you're welcome to do the experiment at your home, always in the presence of a relativist or a quantum mechanic. Take two tops and spin them in the same direction, okay? It's important to do it in the same direction, and see if one attracts the other, okay? And then put them in opposite directions, see if they repel each other. This explanation's underlying quantum physics are fairly complicated. I like this part because here this is the fine print. This explanation is underlying quantum physics are fairly complicated, and without them, the idea of magnetic attraction can be mystifying. Yeah. So it's not surprising that people have viewed magnetic materials with suspicion for much of history. In other words, they have no clue. And that's why, I like to say that he who cannot explain how a magnet attracts another is not a physicist, because we learned that in the first week of classes at the bgaede School of Physics. So maybe you should take a course there, okay? Maybe you'll find out how a magnet physically attracts another. Okay? And yeah, it has little to do with spinning of tops. Maybe it's spinning of threads. Maybe that's what those lines are, those lines of force are. In fact, here we have the version from the bgaede School of Physics. Here it is. Okay, very simple. Okay, here's two magnets that attract each other. Why? Because their threads are spinning in the same direction, clockwise at the top, counterclockwise at the bottom. And now we reverse them. Now you reverse the spin of the threads. Some go clockwise, some go counterclockwise. Again, clockwise and clockwise at the top, clockwise and clockwise at the top, and counterclockwise at the bottom. We turn it around. Now we have north against north, and we have clockwise versus counterclockwise, and they push each other away. So now we have a mechanism, okay? Now, people say, well, I don't believe in your mechanism, Bill. Well, I don't care. That's religion. Whether you believe in something or not is irrelevant. I've got a mechanism that you can understand. You say, well, I don't understand it. Well, then you got a problem. Then you got a mental problem, because it's like, I'm pulling on a rope through a pulley and the box goes up. And I show you, look, this is how the box came up. I pulled on the rope. Okay, I show you every bit in front of you. You got a box, it's tied to a rope. The rope goes around the pulley. I'm pulling on the rope, and the box goes up. Did you understand the mechanism, how the box went up? And if you say, well, no, I don't understand your mechanism, I don't believe in your mechanism. I just showed it to you. I mean, it's not a question of belief, it's a question of did you understand it? And this is the same thing. Here you have, let's do it here. Here you have, these guys hitting each other, that's repulsion. And here you have these guys going in the same direction. When one comes down, the other one comes up, and you have attraction. What part did you understand? There's your mechanism for attraction. And the threads match the lines of force, the Faraday's lines of force. So the question is, what part did you not understand? That's the issue. If you understood the mechanism, I'm done. I'm done with physics. Whether you believe or not, whether you agree that there are ropes or threads out there or particles or waves, that's a separate issue. The issue is that I've explained to you a mechanism, a physical mechanism of how Mother Nature could be doing attraction and repulsion. If you didn't understand the mechanism, I'll do it again. I'll do it 100 times until you understand the mechanism. Okay? That's the issue. And so I do have a mechanism. If you have a better mechanism, hey, bring it on. Especially if you're doing it with particles. I really like to see you do it with particles. Attraction with particles, throwing stones at each other. Got to see that. Okay, last fellow here, and he got his in, 1920? And what did he discover, invent, or what could he explain? Let's see. It says his name is Charles Guillaume, and says, in recognition of the service he has rendered to the precision measurements in physics by his discovery of anomalies in nickel-steel alloys. What did he discover? Succeeded in finding an alloy of nickel and steel that registered almost no change in length and volume as a result of temperature changes. In other words, if you heat a metal, for example, it expands, okay? And when you cool it, it contracts. And he invented an alloy that has resistance to expansion and contraction. That's an invention. Maybe he got it maybe he stumbled upon the discovery, for all we know, and his invention. Is that physics or is that technology? So we got a problem with all these people because they're considered physicists. They're getting Nobel Prizes for what? Physics. And what they're doing is mathematics, okay, and inventions. They're doing descriptions and gadgets. They're going to the lab, doing some kind of experiment, blind because they can't see the invisible stuff. They can't detect the invisible stuff. They can only detect the visible stuff. And then they're inferring that what's happening there is particles and waves. And waves is not a physical object. Wave is what something does. Particles, quantum says it's nothing. It's there's no physics. It's not a corpuscle. That's why you don't see any pictures of particles in the standard model of quantum mechanics. When you look at particles, you'll find the particles there, but you'll find little letters. You won't find a picture of the particle. Look, we were able to take a picture of the particle. And again, people say, well, Bill, you can't expect them to see a particle, a subatomic particle. Well, first of all, they brag that they've filmed, photographed, and interviewed every atom. You know, they show you these atoms from a bird's eye perspective. They say, we took a picture of the atom. And everybody just repeats that. Oh, scientists, the scientists, they have taken pictures of the atom. Yeah, I mean, they took a picture from 500 miles away. That's no good. Then they supposedly smash them inside their bubble chambers, okay, that we showed a couple of weeks ago. So they smash them, they get these particles. They say that the debris that came out of the explosion, out of the collision. And they say, well, see this trace, this one's called Johnny, and this one's called Tommy, and this one's called Jimmy. Okay, so why don't you take, because these particles allegedly make a trace through the gas. Okay, so that's what they say they're looking at. Of course, this is all simulated with computers. It's not like they really took a snapshot of the trace. It's simulated with computers. But if they've got a trace through the gas, all they have to do is measure the width of that trace, and that's the diameter of your particle. If it's a sphere, right? So they have a way of, if what they're doing is correct, they have a way of determining what the diameter of these particles are just by measuring the width of the trace through the gas. So don't tell me that you don't know what these particles look like, because they have all the tools if they're really particles. But they're not going to do that because they don't deal with it. They don't deal with structure. What they deal with is math, and what they deal with is particles. No matter what, it's always particles, because they can put values for a point particle in an equation. They can't put corpuscle in an equation. They can't say corpuscle times corpuscle gives me X. They can't do that. So they put a value, they put energy, they put mass, they put some field or whatever. You know, they put a value there. And so this is where the problem is. They're doing a lot of math, but they have no idea of the real world, the Mother Nature's invisible world. And the question is physics about, you know, this, about telling me what thing is in there that is affecting visible, tangible things? I mean, there had better be some physical entity in this region. You can't just put a concept in there. You can't put a mathematical equation in there. You got to tell me what physical entity is producing this effect, because it's coming in touch with physical things that I can see and touch. So there had better be something, you know, between the two magnets. You just have to identify that invisible entity. That's all we had to do all these years. And once you do, it's once you identify that, it's kid stuff, baby stuff, kindergarten stuff. Okay, because again, you can explain it with threads swinging around, which is what comprises a magnetic field. We're done. You know, you have an explanation of how Mother Nature runs her shop.